Greetings, traveler. I am the calculus cleric, and today we'll be working with convergence of series with positive terms. So the specific question is to use the limit comparison to evaluate convergence, specifically of the infinite series starting at 3 of 3n plus 5 all over n multiplied by n negative 1 multiplied by n negative 2. Normally in this scenario, you would use an integral test and then do partial fractions, but sadly we have to use the limit comparison. We need to set one of our values of an and bn to the original an sequence inside this part. And our bn is what's going to be the tricky part. When we factor this all together, which will make it actually surprisingly easier to solve in the end, n squared minus n minus 2n plus 2 multiplied by n. Okay, so because we're going to be working with limits, that might be more helpful. But now we actually have to determine what our b of n is. And so my hint for you when we work with b of n is to drop all the constants, and on the denominator, the highest degree is what we keep, and we just drop everything after it. It'll make it a lot easier to evaluate in the long run. You could pick a different value if that doesn't work for you, but that's like my go-to solution. So the highest value is n cubed. When you evaluate convergence later after y and use b of n to evaluate the convergence, it's a lot easier if there's no constants in it whatsoever to evaluate convergence or divergence. Otherwise, you're pretty much just going to be stuck to the integral test to determine convergence or divergence with an added constant on it. So after I drop everything that leaves me with that, these will simplify out. So that's 3 over n squared. So your b of n term can be anything as long as it's really simple and easy to evaluate, and it works out so that when you take the limit comparison, your b of n is what you use to determine convergence, not your a of n value, because that's just the original series. And if we're just going to evaluate the original series by using itself, we wouldn't bother with the limit comparison test. 3n plus 5 over n cubed minus 3n squared plus 2n multiplied by n squared all over 3 because a of n over b of n. So I flip the fraction. Multiply all this out. Well, when we plug infinities in, it's clearly infinity over infinity. So now we need to take L'Hopital's and find the derivative of the top and the bottom separately. 9n squared plus 10n all over 9339n squared negative 18n plus 6. And it's infinity over infinity again, so we have to keep going until it's not indeterminate. 18n plus 10 all over 18n minus 18 is equal to limit as n approaches infinity. One more time of 18 over 18, which is equal to 1. When we take the limit as n approaches infinity of an over bn, we get 1. Now, according to the limit comparison theorem, which is why I have this L over here, if L is greater than 0, then we can either use an or bn to determine convergence or divergence. So basically, we can pick whichever one of the two that we prefer, which is why getting a L value of greater than 0 is the best one to get. Okay, so I'm going to pick our b of n because it's obviously much simpler. And as I told you in the beginning, that's why we even make a b of n in the first place. That is our new series that we're evaluating. And this is equal to that. And we can ignore the constant. So we know this interior part converges by the p series because p series is written as 1 over n to the p. And when the p is greater than 1, then the series converges. And because the p over here is greater than 1, we know this whole series converges. So we know that therefore our original function, which is equal to our a of n, converges by limit comparison.